left off with question 13.16 and 13.18. And let's take a look at the next two in 13.16. So again, all of these involve strong nucleophiles. So the next one we have lithium aluminum hydride. So we have hydride, which is a strong nucleophile. I'll just draw the whole aluminum hydride ion out. So to know how to draw its Lewis structure. So there's the negative charge. Again, it's a strong nucleophile, so it's going to attack the least hindered carbon. It's going to attack here. We open up the ring. And then after the proton transfer, so I guess we could draw both steps. So we end up with something that looks like this. Here's our alkoxide, like this. We have our methyl group over here. And then remember, there were initially 2 protons on this carbon. And now all you did was add a third one. So now it's just a methyl group. So after the proton transfer from the hydronium, I'll just write PT for proton transfer. What you end up with is this compound, okay, which is isopropanol, but there's no stereocenter in the compound. So it's the same thing as just saying isopropyl alcohol, because there's no stereocenter in the compound. All right. And then the next one, we have ethoxide as our nucleophile. So I'll draw ethoxide out like this. It's going to attack the least hindered carbon. So it's going to attack this side here. We open up the ring. We're going to draw our alkoxide. So we have the oxygen with our negative charge over here. I'm just going to write pH for the phenyl. And we have our ethyl group over here. And we have an ethyl ether over here. And then we have the proton transfer. And the next step, this time I'll draw out the whole mechanism. So here's our hydronium. Pick up the proton. And let's draw the final product. So I'll draw it as a bond line structure. So we have our oxygen here. We have an ethyl group. Then we have our alcohol over here. We have our phenyl, which is in the back. And then we have an ethyl group, CH2, CH3, which is coming off like this. And there you go. There's the final product. So again, strong nucleophile, we attack the least hindered carbon. The next one that we didn't cover, the first step is going to be to protonate the oxygen in the ring to render the ring more electrophilic. So I'll put my proton here. And if I highlight this carbon in green and this carbon in blue, can anybody tell me where is the methanol going to attack? At the carbon in green or the carbon in blue? Anybody? Yeah, because it's tertiary. Exactly. It's going to attack the carbon in green. Thanks. Great. So we'll draw our nucleophilic attack. So here's our nucleophile. It's going to attack like this, right? It's going to attack from the opposite face. So we end up with something like this. And now the 5-membered ring, instead of pointing down, it's going to point up. So we're going to have our hydroxyl group here. We have our methyl group here like this. We're going to have in the back and in the front, here's our 5-membered ring. And then down here, we have our oxonium ion. And then in the next step, you could draw water as the base. You could draw methanol as the base. It doesn't matter. I'll draw methanol as the base. And so that's going to pick up this proton here. Sorry, I couldn't see, so my arrow's a little funny looking. Anyhow, and I'll just copy and paste this and then fix it up. So there we go. All right, so our final product is going to look like this. We'll do all that spinach. And then we'll just put our methyl group is right there. And there you go. So that covers ring opening. Does the methyl group preserve its stereochemistry? Yes. So both. So if you're, I'm not sure which one you're referring to, this one or this one, right? There's no reaction at that chiral center, right? There's nothing happening there. And so, yes, it's still going to be pointing out. Okay. You only get a flip if it's attacking. Right, so yeah, so this one, so in the second one, and this one here, you didn't touch that methyl, so maybe you can't see it, but this is supposed to be a wedge like that. We'll make it a little more pronounced. There we go. All right. There we go. So that covers ring opening. And so the part about thiols and sulfides, it says to skip it, but I want to cover a little bit of it with you. I think it is important that you understand what a thiol is. So a thiol is the sulfur analog of an alcohol, and a sulfide is the sulfur analog of an ether, like this, right? And you guys know that sulfur comes below oxygen in the periodic table, and so it's significantly bigger. So going back to the idea of the thiol group, if you want to name a thiol, it's actually pretty straightforward. All you have to do is use the alcohol nomenclature, but you don't drop the E at the end of the parent chain. So here you'd have 3-methyl-1-butanol. So here you'd have 3-methyl-1-butane thiol. You just replace all for your alcohol with thiol. That's all there. No pun intended. That's all there is to it. Anyhow, another name for a thiol is a mercaptan. So if you're like, what the hell is that supposed to be? The captain of what? Now, they call it a mercaptan because sulfur can bind to mercury and capture it. So that's where it comes. That's where mercaptan comes from. If you're poisoned with mercury, they'll give you a sulfur-containing compound that helps to bind to the mercury, and then it can get excreted from your body. But yeah. Anyhow, so I would recommend reading through the part about thiols and sulfides. I don't think it's a bad idea. So I'll just put on it. I'll put read through. So read through, just, for my students who are interested in things like MCAT or DAT, sometimes they add thiol questions in it, but they're not in the ACS, but they are covered in MCAT sometimes. So again, I teach the class to the ACS exam. So as far as synthesis strategies with epoxides go, this section, it can be challenging. Okay, this section can be challenging, is looking at synthesis strategies. But, if you think about it, the epoxide has how many carbons? 1, 2 carbons. And so if you need to install 2 carbons and then a functional group like an alcohol, an epoxide is a really good choice, right? So it's something you have to look for all the time. Also, if you see 2 functional groups next to each other that come from, that could come from an epoxide, that's a good way to make it. So here you have an alcohol, and then you have a nitrile right next to each other. So you could think epoxide. So I'd make the epoxide with MCPBA, which after step 1, you would have this compound. So if I just draw out the intermediate that you would have, you'd have something that looks like this. Okay, and stereochemistry is not really covered. It's not that important that I draw it. But anyhow, so you'd have the epoxide, right? That's after step 1, and then you could hit that with cyanide, right? And the cyanide, Cn minus, is going to attack at the least hindered site, and then you're going to end up with this as your final product. So you see a nitrile and an alcohol next to each other. So it's something you just have to look for, Another one that I feel like this is not covered before this section explicitly, but you can also use an epoxide with a Grignard, right? So if you take an alkyl halide and you treat it with magnesium and diethyl ether, right? After step 1, what are you going to have? You're going to have RMgBr, let's say, something like this, okay? Well, then what's that mean? You have a really good nucleophile, and you're going to be able to do a nucleophilic attack like this. After a proton transfer, you end up adding 1, 2 carbons. So whenever you see a chain increasing by 2 carbons, you can oftentimes think of using an epoxide to do that, okay? So there you go. So you see that kind of written out here. It says the epoxide consists of a carbon chain that will be added to the alkyl halide. Now, I have a retrosynthetic way of doing this that I'll show you in a little bit, which is not anything official. It's just the kind of a way I do it sometimes, but I'll show you that in a second. So an epoxide yields a longer carbon chain, while a functional group on the second carbon of the with a functional group on the second carbon of the newly installed chain. However, if you were to do a Grignard and then use a carbonyl-containing compound, like this one here, this is called acetaldehyde, this compound here. In that case, you'd end up with your functional group on the first carbon. So you can't always use an epoxide every time you see 2 new carbons. It depends. If the functional group is on carbon 2, yes, probably an epoxide. But if the functional group is on carbon 1, then probably not an epoxide. So again, it just requires you to practice it over and over and over. So let's say you wanted to do this reaction here. You wanted to take bromobenzene, and then you wanted to make this secondary alcohol. How are you going to do this? So this is not something official from the organic chemistry or the textbook or anything. It's just the way I show my students. And that is, you notice that you have 1, 2, 3 carbons coming off of the ring, and that the functional group, the alcohol, is on the second carbon. And so you probably think that I need an oxirane, right? But then if you're like, well, what's the oxirane going to be? So here's the way I do it. It's kind of Mr. Dion's retro synthetic way of doing it. And I'll draw it down here. And again, this is not official or anything. I just find it's the simplest way to get the right epoxide. So, oops, don't even have my hydroxyl in the right place. There we go. Okay, so you do this, and then you kind of go backwards with your curved arrows, and you make a bond or draw a curved arrow, which is not a correct curved arrow, but you could draw a bond between the lone pair and the first carbon attached to the ring, and then say break that. And then this shows you what the epoxide should be, right? You see you have a bond like this, right? That is this part here, and then you have a methyl group coming off of it like that. So you need 2-methyl oxirane as your electrophile. I hope you find that useful. So what the overall synthetic pathway is going to be is to first treat this with magnesium. You can put diethyl ether, okay? That's going to make your Greenyard reagent, which is going to look like this. So we have, I'll draw it as a carbanion. It's just the way I like it. So something like this. And then we can draw the epoxide, okay? The one that I have in yellow, I'll just draw it out like this, okay? So 2-methyl oxirane. And if you want to practice your curved arrows, you could say nucleophilic attack. It's a strong nucleophile, attacks the least hindered carbon, right? That's going to give me this compound. I'm going to end up with something that looks like this. Okay, like that, right? If you need to number the carbons, there's no shame in that. Look, 1, 2, 3. Okay, so the bond is between the aromatic ring and carbon 1, 2, 3. And on carbon number 2, that's where the oxygen is attached to. Just forget my negative charge here. So negative. And then in the last step, we're just going to treat it with H2O or H3O plus. Either one is fine. And you're going to protonate it like that. So again, this is just my kind of unofficial way of coming up with what the actual structure of the oxirane or epoxide is. And give me a thumbs up if you follow me on this synthesis. Yeah, cool. Awesome. And again, if you're practicing and there's any questions in the textbook and you're like, how did they get that oxirane, just shoot me an email and I'll be happy to help you figure that out. So, what's the overall process? Step 1 is going to be magnesium and ether to make your Greenyard. Step 2, there's your oxirane. And step 3 is going to be aqueous workup with aqueous acid. And there you have it, like that. So let's say you wanted to do this first transformation here. Okay, we have an alcohol and then we have a nitrile on the same compound. And just to refresh your memory, if we go all the way back, we have to go back a little bit here in our slide. So just bear with me here. Sorry. I'll go back to that slide where it says, oh, you got a lot of reactions on the same slide. This one here, if you need a nitrile and an alcohol in the same compound, what are you going to do? You're going to make an epoxide, and then you're going to hit it with a cyanide, right? And then that is going to put a cyano group or a nitrile and a hydroxyl on carbons 1 and 2 respectively. Anyhow, so let's go back to the problem and let's see if we can apply that strategy right here. Okay, so I'm going to scribble this down. So we're going to start out with our compound. So this is 2-methyl 2-butene. What's our first step going to be? Can anybody provide me with the reagent we will use to make the epoxide? And it's not a trick question, just practicing. Just fleshing the idea out. Anybody? Yeah, exactly. MCPBA, thanks. MCPBA, perfect. So let's put that in here. So now we're going to have our epoxide like this. Come on, pen. So now we're going to have our two methyl groups like this. We're going to have our cyano group here. Now remember, cyanide is a strong nucleophile, so it's going to attack this carbon because it's the least hindered carbon. And so then we're going to treat it with sodium cyanide. So I'll put Na plus Cn minus like this. So we're going to get our nucleophilic attack, opening of the ring. That's going to give us this. So there's our alkoxide, two methyl groups. There's our nitrile, and then in the last step, we're going to treat this with H3O plus or water. Either one is fine. And you're going to proton transfer. Proton transfer like that. And there you go. You get to the final product. All right. Next one. Oh boy. Let's see how powerful our memories are. And that means me too. So for this one, we're starting with an alkane. Right, you guys know this compound. This is just cyclopentane. If I'm starting it with cyclopentane and I want to make a transdiol, who remembers from Organic Chemistry 1, if you're starting it with an alkane, what does the first step have to be? Does anybody remember this one? The first step has to be something. Yeah, thanks, Kristen. It's going to be bromine and light. Yeah, thanks, Mustafa. Thanks, you guys. Awesome. Heck yeah. So we're going to start out with bromine and light. I just wanted to test you on that one to see if you remember. Absolutely. So that would give you bromocyclopentane. Okay, and I think that you guys know that retrosynthetically, right, that the transdiol has to come from the alkene. So that means we have to convert this compound into an alkene somehow. Well, in that case, we're going to use a hindered base, right, because it's not going to do a nucleophilic attack. It's just going to do an elimination. So I'm just going to choose potassium T-butoxide. If you chose DBU or DBN, either one of those are fine. We end up with the alkene. And then to make the transdiol, step 1 is going to be MCPBA, and step 2 is going to be H3O plus. Boy, oh boy, this is a real nostalgia here. This is a reaction that we looked at a lot in Chemistry 3101. And then this process here, we learned that in Chem 3101 as well. This is kind of old chemistry. Actually, this whole dang thing, what am I talking about? All of these come from Chemistry 3101. There's actually nothing new in this one. Anyhow, I digress. Okay, let's try. This is the last slide in the chapter. Let's see if we can solve these here. So the first one we're starting it with, actually all three of them, we're starting it with bromocyclohexane. But in this one, if I count my carbons, 1, 2, my functional group is on the first carbon. And so I'm probably not going to use a epoxide in this case. I'm going to use a carbonyl compound. And so what's the carbonyl compound? I'm going to have a double bond for my oxygen to carbons 1 and 2. And so that is going to be my electrophile. So you see that it's actually an aldehyde. And so what are we going to do? We're going to take the bromocyclohexane. We're going to treat this with magnesium and diethyl ether to make our Grignard. So here is the Grignard reagent, like this. Then we're going to treat it with our aldehyde, which is this aldehyde here. We're going to get a nucleophilic attack like this. That's going to give us this compound, this alkoxide. And then to get the final product, so to get from here to here, you can just treat it with H3O plus or water. Either one is fine. Now the next one, you see that we have carbons 1 and 2, and you see the functional group is on the second carbon, so that suggests we're going to use an epoxide. So again, if you want to know my kind of shorthand version of it, the way I figure out what the epoxide should look like is I draw a bond between carbon 1 and the oxygen, okay? So that is my epoxide, okay? It might be kind of a little warped the way I drew it, but let me try to draw it in the same perspective here. So you have your oxygen, Okay, you've got your 3-membered ring like this, and then you have 2 methyl groups coming off of it like this. So you have 2,2-dimethyloxyrene, which is going to be your electrophile in this case. Now here I'm kind of running out of blank space, so what I'm going to do is I'm just going to write down the steps. The first one would be magnesium and diethyl ether to make your green yard. The second one, and again I'm really running out of space here, would be the 2,2-dimethyloxyrene, and then the third one would be protonation with H3O plus. And then in the last one, again, we have, if you count the carbons 1, 2, like this, you have the functional group at carbon number 1, and this is a ketone. If we made it from an alcohol, all we would have to do is oxidize it with PCC or something. And so I will just kind of create a little box for this one here, just so there's no mix-up. And then for this one here, something like this. So what's the overall scheme going to look like? Is we're first going to make our Grignard reagent. So we end up with a carbanion. And then our electrophile in this case is going to be what? It's going to be this aldehyde, where we have something that looks like this, and then that's going to produce this alcohol. So step 1 would be this, step 2 will be H3O plus. We're going to end up with this alcohol. But then to get to the final product, all I have to do is treat it with PCC, and you oxidize it, and there you have it. So that covers all of chapter 13, the whole thing.